Now we move on to another class of identities called the sum and difference formulas. And I've listed 3 of them on the board that are in your notes, but just so I don't want to use up too much room writing all of them down. So if you look in the notes, cosine of A minus B is cosine A cosine B plus sine A sine B. If I change the minus sign to a plus here, the plus sign turns into a minus here. Likewise, sine of A minus B is sine A cosine B minus cosine A sine B. If I do a plus here, sine A plus B, this turns into a plus here. And tan of A minus B is tan A minus tan B over 1 plus tan A tan B. If I put a plus sign here, this one turns into a plus, and this one turns into a minus. Okay, so that way I can have them, and we can have them in front of us as we go through the lecture. Okay, so the first example says, use the calculator to verify that the formulas work for A is 23 degrees and B is 17 degrees. Now, I don't think we need to do all 6. Let's just do a couple here. So, for example, I'll just use the one here in blue, cosine A minus B. So, I'm going to let A be 23 degrees, and I'm going to let B be 17 degrees. So, I'm going to leave a little room here in front. I'm going to add something to it. This says cosine of 23 degrees minus 17 degrees, A and B. That is cosine 23 degrees, cosine 17 degrees, plus sine of 23 degrees, sine of 17 degrees. Okay, so I'm just recopying this formula here in blue. A is 23 and B is 17. Okay, now let me work back this way a little bit. Well, 23 degrees minus 17 degrees is just 6 degrees. So this should be the cosine of 6 degrees. All right, so let's just punch in the calculator. I'm going to punch in cosine 6 degrees and see what I get, and then punch that expression in and see what we get. All right, make sure when you type this in, you're in degree mode because of the angles here are in degrees. Now, okay, so I'm going to do this one. Cosine 23 degrees times cosine 17. Again, you should punch in too. Don't just watch me. You should do it too. Plus sine of 23, sine of 17. And I get about 0.9945. Now the claim is that these identities are actually identities, so if I type in cosine of 6 degrees, I should get the same thing, and I do. Remember, for identities, if you plug in the same thing for A on both sides and the same thing on B on both sides, you should get the same answers on both sides, as long as both sides are defined. I mean, identities, you can get an undefined on one side and a 6 on the other, but we still call it an identity because we only expect them to be equal when both sides are defined. Let's do the tangent one. Let's do tan of A plus B. So I'm using tan of A plus B, so I'm using the black formula here. With A is 23 and B is 17. Again, let me leave some room here. So tangent of 23 degrees plus 17 degrees, that should equal tangent of 23 degrees plus tan of 17 degrees divided by 1 minus tangent of 23 degrees, tangent of 17 degrees. And so I'm using the black formula here. So tan of A plus B is tan of A plus tan of B over 1 minus tan A tan B. Right. Okay, so let's type in the right-hand side here. I'm still in degree mode. And again, especially with this quotient, you should punch this in too. I'm getting about 0.8391 if I round to 4 places. Now, if you want to type this entire quantity into your calculator in one step, you need to put the entire numerator in parentheses and the entire denominator in parentheses. Or it's going to do tan of that plus tan of that divided by 1, and then it will subtract that from it, and that's not right. So whenever you have a quotient, you might just get in the habit of putting the entire numerator in parentheses and the entire denominator in parentheses, whether you need them or not, and then if you have them extra, it's no big deal. Now, what should this equal? This should be tan of 23 plus 17 degrees is 40 degrees. So let's see if I got that right. Yes, and that's also 0.8391, which we expected it to be. Okay? Now, these formulas are true whether your angles are in degrees or radians, okay? So if I had done, picked an angle A and B in radian measure and done the same thing, you'll get the same answers, okay? But not if I did 23 radians, 17 radians, 23 radians, 17 radians. I'm not going to get that answer, but I'll get the same answer here that you get over here. If I did cosine of 6 radians and then that, I'll get the same answer, but it's not going to be this one. Okay, so hopefully this kind of gives you an idea that we're in good shape here. So what do these identities do for you? Okay, notice the relationship here. If you knew sine and cosine of 23 degrees and 17 degrees, you can use that to find the cosine of 6 degrees. Likewise, if you know the tan of 23 and tan of 17 degrees, you can use that to find the tan of 40 degrees. So it's trying to relate an angle that maybe you don't know to angles that maybe you do know something about. Okay? So that's the idea here. It's turning a problem into, I don't know the cosine of this angle, but I know the cosines and sines of these, so I can use these to find this. Right? So that's where we're headed. And so this next example is illustrates that. Now think about what angles up to this point, before this section, we could find the sine and the cosine, the trig functions of without a calculator. Right? Quadrantal angles we know how to do with the unit circle, right? Pick the point 1 u away, 1 0 0 1 minus 1 0 0 minus 1. The x value is cosine, the y value is sine. Use reciprocals and quotients to get the other trig values. Right? Or if we have an angle whose reference angle is 30 degrees, 60 degrees, or 45 degrees, we have our special triangles for those. Okay, that's all we can do right now. Well, until this section. So the next example is find the exact value of cosine of pi over 12. Right? Now, how do I know that this angle is not a quadrantal or special triangle? In other words, we can't do it from methods we've already learned. Okay, so in radian measure, it's easy to see whether your angle is a quadrantal or not. Quadrantal angles in radian measure with a simplified fraction, first of all, you have to have a pi. If the denominator is 1 or 2, it's a quadrantal. So this is pi over 12, it's not a quadrantal. If it's pi over 2, or 8 pi over 1, right? Or 121 pi over 2, I know that's a quadrantal. Okay? But this is not. Now, how do you recognize whether in radian measure an angle is you can use with special triangles? Well, the denominator, if it's simplified, needs to be a 3, a 6, or a 4. And it's not. Now be careful, if this were 3 pi over 12, that would simplify to pi over 4, so you could use special triangles. But this is already a reduced fraction. It's 1/12 pi, so this is not a special triangle. So it's neither a special triangle problem nor a quadrantal problem. Well, what do? Right? That's the dead giveaway. It's a problem from this section. I always have students on the final exam who you give a problem like this and they try to use special triangles and none of them work and they don't know what to do. You have to remember it's a problem from this section. Now, I've been cautioning about whenever you have radians, don't convert to degrees. Almost every problem in calculus where you have trigonometry, you're assuming the angles are in radian measure, and there's a good reason for that. Right? So I've been trying to get students in this course to think of things in radians, because in calc everything's in radians. But here's an example where it's really important. It makes it easier if you do actually convert to degrees. So I'm just going to do this as scratch work. So pi over 12 radians times, right? I want to get rid of the radian units, so those go in the denominator and degrees go on top. I want the radians units to cancel. And now how many degrees is how many radians? 100 degrees, 180 degrees is pi radians. Okay, and so the pi's cancel and you get 180 over 12, and I believe that's 15. Okay, so this is the same. Now, I'm not saying this whole thing is 15 degrees, just this angle. So pi over 12 is the same thing as 15 degrees. Okay. Now, hopefully you realize for sure we don't have a special triangle. If you forget, I mean, you'd say, oh, okay, let's draw the triangle, 15 degrees. You have no idea what to put on the sides, okay? Because it's not a special triangle. Okay, so this is going back to what I was just discussing a little while ago about when we had the 23 and the 17 and the 6 degrees. I don't know how to find cosine of 15 degrees. Okay, that's like the 6, right? Or the 40 degrees we had before. Can I rewrite 15 degrees as a sum, we're doing cosine here, as a sum or difference of two angles we do know about? Okay, so that's the game here in this section. I don't have a special triangle to give me cosine of 15 degrees, but can I rewrite 15 degrees as a sum or difference of two angles which we can compute the sines and cosines of without the calculator? And there's a couple of possibilities, but I'm just going to, the first thing that occurs to me is do 45 degrees minus 30 degrees. 45 degrees minus 30 degrees is 15 degrees. 45 degrees is an angle in the special triangle, and 30 degrees is an angle in the special triangle, so I know I can do those. Okay? It doesn't do, I mean, this is certainly a true statement. This is also 20 degrees minus 5 degrees, but that's not going to help me because I don't know how to do cosine and sine of 20 degrees and 5 degrees. Okay, so you need to pick two angles here that add or subtract to that angle, and those two angles you can do without the calculator. So the reference angle needs to be 30, 60, or 45. Now, it doesn't do you any good to pick a quadrantal here, because if you pick a quadrantal and say, this is cosine of 90 degrees minus something, if you can't do this one without the calculator, you're not going to be able to do this one either. Okay, so don't pick a quadrantal here. If you're not going to make it's not going to make your life any easier. In fact, you've made it harder on yourself. Okay. Okay, so according to the formula, what's cosine of A minus B? Cosine of A minus B is cosine A, cosine B, plus sine A, sine B. So I'm using the blue formula here, right? Cosine of A minus B, that's what I have here, is equal to cosine A, cosine B, plus sine A, sine B. Right? Now there's four things to find here. Right? There are four things to find, but we know how to find these because we have a reference angles here of 30 and 45 degrees. Right? So 45 degrees, right? That's an angle in the first quadrant, 45 degrees. And our special triangle, it's 1, 1, square root of 2. And so let's go ahead and fill in what's the cosine of 45 degrees. It's adjacent over hypotenuse, so that's 1 over root 2. Sine of 45 is opposite over hypotenuse, 1 over root 2. Now we need to do the same thing with 30 degrees. There's 30 degrees in the first quadrant. Again, my picture is not to scale. And the three numbers on the special triangle were 1, 2, square root of 3. Right? If you can just remember the three numbers, you can figure out where they go, because 2 is the largest number. It has to be on the hypotenuse. 1 is the smaller number of the remaining two, so it has to be opposite the smallest angle. There's a 60 degrees here, that's 30. 1 is opposite 30. And now we can do cosine and sine. So cosine of 30 degrees is adjacent over hypotenuse, square root of 3 over 2. Sine of 30 is opposite over hypotenuse, 1 over 2. And then we just multiply our fractions, but don't forget to multiply, right? To multiply fractions, multiply numerators, multiply denominators, you get square root of 3 over 2 root 2. Plus 1 over 2 root 2. And to add fractions, you need a common denominator, which we have. And so you get square root of 3 plus 1 over 2 root 2. Again, if you want to rationalize, you multiply by root 2 over root 2. And then work it out. Okay, so that's the cosine of pi over 12, or cosine of 15 degrees. It's root 3 plus 1 over 2 root 2. Right, so we can't actually find values, trigonometric function values of some angles, right? As long as you can write the angle as a sum or difference of two angles we already know how to do, we can get some new values that we couldn't get before. Okay, the next example is similar. It says find the exact value of tangent of 345 degrees. Tangent of 345. Okay, tangent of 345 degrees. So this one's already in degree measure. Notice on the last example, the problem that was given, it was pi over 12, right? It was pi over 12. We rewrote that in degrees, which was 15 degrees, and then we wrote 15 as 45 minus 30. So what is 45 degrees in radians? It's pi over 4. 30 degrees is pi over 6. Now, do you see why I converted to degrees? Because trying to figure out that pi over 12 is pi over 4 minus pi over 6 is not so easy. It's not so obvious. Okay? It's easy to see, oh, 15 is 45 minus 30. Those are two angles I can do. I know I can do pi over 4 and pi over 6. The denominators are 4 and 6, like I mentioned before. But it's not obvious that pi over 12 is the difference of those two. So that's why I went ahead and converted to degrees. Okay, now tangent of 345. Now, if this is a problem on the final exam and you don't know what section it comes from, I mean, you might want to let's just do a rough sketch. Where's 345 degrees? That's in the fourth quadrant. No problem. 345 degrees. Now, what's the reference angle of 345 degrees? Well, to get to 360, you're missing 15 degrees. So again, this is not a special triangle that we know, so you can't do it from the methods we used in previous sections. Okay. Okay, so that's how you can figure out, is it from something we did a long time ago, or is it something new? So this is in the new section, because 15 degrees we don't have a special triangle for. So what do we need to do? We need to rewrite 345 degrees as a sum or difference of two angles that we know we can do. Now, obviously you can't just put a 45 and a 30 here. You're not going to get 345, right? And don't make them add up to 30 or whatever it was. The 15, right? Don't do tan of 15, right? The angle here is 345, not 15. Right? Tangent of 15 is positive because 15 is in the first quadrant. Tangent of 345 is going to be negative, okay? So I want two angles that add or subtract to 345, not the reference angle. Okay, now remember the two angles we need here have to have reference angles of 30, 60, or 45. So what I typically do is just pick one of the angles, one of those three angles, 30, 60, or 45. Suppose I pick 30 degrees. I'm just picking 30. Now if I do a sum here, what angle would have to go here to add up to 345? Well, it'd have to be 315, wouldn't it? Okay, I just picked 30, right? And what would have to go here to make the sum 345, 315? I know I can do trig function values of 30 degrees. Can I do 315? Well, let me draw the picture again. 315 is also in the fourth quadrant. Now, what's the reference angle of 315 degrees? That's 45 degrees, and so I can also do 315. Okay, so that's what I do. I just pick 30, 60, or 45, figure out what angle needs to go here, and then I see if I can do that angle with special triangles, and I can. The reference angle of 315 is 45. Okay, I'm going to leave that picture because I think we're going to need it. So now I have tan of A plus B. I'm using the tan of A plus B formula. That's tangent of A plus tangent of B over 1 minus tangent of A tangent of B. Okay? So the hard part here is just figuring out how do you break up this angle into the sum or difference of two angles that we can do. All right? So again, I just got lucky. I picked 30, and it turns out what I needed here was, worked. Okay, so now there's 4 things to find here. There's 4 blanks to fill in, but there's only 2 different things. So even though it's a quotient, the tangent form is a lot more complicated than sine and cosine, but in these 2 forms, there's 4 different things to find. Here, there's only 2. All right, so there's my picture for 315. I need the tangent. Well, this is my special triangle with 45 degrees, so it's 1, 1, square root of 2. And don't forget to check for negatives, right? This side has to be negative. Now, what's the tangent of 315? It's opposite over adjacent. So that's -1. And tan of 3, -1 here as well. And then tangent 30, well, I have my picture for 30 degrees here. What's the tangent of 30? It's opposite over adjacent, so that's 1 over root 3 and 1 over root 3. Right? Now, never leave fractions in fractions. That's terrible. Okay, so we want to simplify. All right, so let me simplify what I have to get rid of all these parentheses. So in the numerator, I have -1 plus 1 over root 3 over 1. The negative times the negative here is going to be plus, and 1 times 1 over root 3 is 1 over root 3. That looks a little bit better. I just put the parentheses here to save a place for the number. It tells me I have 4 things to fill in. Okay, now how do we get rid of the fractions in the fractions, right? Think of this as being -1 over 1, -1 over 1. Right? So what's the least, look at all the denominators. 1 root 3, 1 root 3. The least common multiple of those is root 3. Least common denominator. So I'm going to multiply by root 3 over root 3. So if you do this, you'll wipe out all the fractions in the fractions. Root 3 times -1 is negative root 3. 1 over root 3 times root 3 is 1. Root 3 times 1 is root 3. 1 over root 3 times root 3 is 1. Okay? And again, I'm perfectly happy with this answer. But if you wanted to rationalize this, what would you have to do? You can't just multiply. There's a root 3 in the denominator. You can't just multiply by root 3 over root 3. If you multiply by root 3 in the denominator, you're going to get 3 plus root 3. The root doesn't go away. It just moves to the other place. Whenever you have an expression like this, and you're trying to rationalize a denominator where it's a sum or difference, right? You multiply by the conjugate of this. So keep the same thing, but instead of a plus, multiply by a minus. That's what you have to do. If this had been a minus here, I would have put a plus here and a plus here. And if you multiply all that out, you'll get rid of the root in the denominator. Again, I'm not that concerned about the rationalization, but an online computer homework system may, so just be aware of that. Okay. Now, on a problem like this, even though it said give the exact value, which is what this is, right? I don't have a decimal. You can check your answer here, right? We were trying to find the tangent of 345 degrees. I'm still in degree mode. Tan of 345 is approximately minus 0.268. If this is not minus 0.268 when I'm punching in, I've made a mistake. So you can check your answer with the calculator, even though they don't want you to use it in this problem. So if I type this in now, be careful. Put the entire numerator in parentheses and the entire denominator. So parentheses minus root 3 plus 1 parentheses divided by parentheses root 3 plus 1 parentheses. And I got minus 0.268. Okay, so we did it right. Right? Same thing on the previous problem. I could have checked it with the calculator as well. Again, they don't want you to use the calculator on the problem. They want the exact value. There's exact value, no decimals. But you can check your answer with the calculator. Nobody would ever know. Okay, the next problem is a little bit different. Okay. The next problem, they give you information about S and T, so let's write that down. So it says sine of S is 2/3. It says sine of T is negative 1/3. S is in the second quadrant. T is in the fourth quadrant. Okay, so that's the information that's given. And they want us to find sine of S plus T. And then find sine of S minus T. Okay? Now think about what this problem is given to you and what it's asking. It wants to know the sine of the angle S plus T and sine of the angle S minus T. Now what information did they give you in the problem about the angle S plus T? This is not a trick question. They give you no information about S plus T. You know about S, you know about T, but they told you nothing about S plus T. You can't say S is in the second quadrant, T is in the fourth, so S plus T is in the sixth. I mean, that makes no sense. You can't just add quadrants like that, right? And you can't just add those two numbers together, right? This is not the same as sine of S plus sine of T. You can't just take that with sine of S, sine of T, and add them together. Don't you think if this were true, that's what our formula would have been? Why have this complicated formula if this were true? Because it's not true, okay? You can't distribute the sign, as students will say, okay? You can't do that. Distributed probably means you have multiplication there. This is sine of, it's not sin times, okay? Okay. Okay, and likewise here. We want to know sine of the angle s minus t. What do you know right now about the angle s minus t? Absolutely nothing. They didn't tell you anything about s minus t. Now, what's the whole point of these formulas? If you want to know about a sum or difference, and you don't know anything about the sum or difference, like we don't know anything about these, what can you do? Rewrite each of these in terms of, here it's, I want to know about cosine A minus B. If you don't know about A minus B, what can you do? Rewrite this in terms of this. If you know about A and you know about B, you can fill those in and it will tell you about this. Okay, so that's the game we're going to play here. So sine of s plus t, I'm using the formula here with the plus. That's sine of s, cosine of t, it's plus, so it's plus cosine of s, sine of t. Right? So sine of s plus t is sine of s cosine t plus cosine s sine of t. So there's 4 things to fill in. And notice, so to find sine of s plus t, I need these 4 things. I need to know about s and t, and we do. Now, we can plug some of these in without doing any work. They told me sine of s was 2/3, so sine of s is 2/3. Now, don't write sine 2/3, right? S is not 2/3, right? If you write sine 2/3, you're telling me s is 2/3. S is not 2/3. I have no idea what the angle is. I know s is in the second quadrant. I know the sine of s is 2/3. So instead of sine of s, the whole thing, you put 2/3. Don't put 2/3 for s. I don't know what s is. And sine of t is negative 1/3. So instead of all of sine of t, I write minus 1/3. I mean, even if you didn't know how to get any further, at least that's a little bit, partial work. Okay? Now we need cosine s and cosine t. Isn't this enough information to draw pictures for s and t? Sure. So s is in the second quadrant. I don't know the rotation. I'm just going to draw something in. Okay? So there's s. Sine of s is 2/3, and sine is opposite the reference angle, opposite over hypotenuse. T is in the fourth quadrant, so I don't know that's a rotation. I just like to put something. There's t. And label your picture so you know which is which. So t is in the fourth quadrant. Sine of t is negative 1/3. That's opposite over hypotenuse. And the negative doesn't go on r. It obviously goes on the y. Well, we know how to find the other side. Just use Pythagorean theorem. I'm just going to skip that. And so use Pythagorean theorem to find the other side. It looks like this is going to be square root of 5. Because square root of 5 squared is 5, plus 2 squared is 4, 5 and 4 is 9, which is 3 squared. But in the second quadrant, the x value is negative. Don't forget to check for negatives. If you do the same thing here, you'll get that this side, use Pythagorean theorem, this side's square root of 8 or 2 root 2, if you want to write 2 root 2. And in the first quadrant, x is positive, so that's good. Okay, now we can use these pictures to fill in here. So what's cosine of t? Cosine of t, I'll use 2 root 2. It's the same as root 8. So cosine is adjacent over hypotenuse. So it's 2 root 2 over 3. And cosine is adjacent over hypotenuse. And what's cosine s? That's adjacent over hypotenuse. So it's minus root 5 over 3. Right? So you use this information to draw a picture of s and draw a picture of t. Once you have those, you can fill in everything here. I still have no idea what s plus t is, but I don't need it. Now let's just do the arithmetic. To multiply fractions, you multiply across, so that's 4 root 2 over 9, and plus, now the negative times the negative is a positive, root 5 times 1 is root 5 over 9, and you add the fractions by leaving the denominator alone. It's a common denominator, 4 root 2 plus root 5. So there's sine of s plus t. Now where could the angle s plus t be? What quadrant could s plus t be in? It has nothing to do with this. Sine of s plus t is positive And where is sine positive? Sine's positive in the first quadrant or in the second quadrant. So I know s plus t is either in the first quadrant or the second quadrant. I don't know which. Okay. Now what about sine s plus t? Well, sine s minus t. Sorry, sine of s minus t. Sine of s minus t is sine of a cosine. Well, let me say it again. T. Sine of s minus t is sine of s cosine t minus cosine s sine of t. What's the only difference between this and what we just did? Instead of a plus here, it's just going to be a minus. So I don't really have to work all that out again. Where's the only difference going to be? This is going to be the opposite sign, isn't it? So we get 4 root 2 over 9 minus root 5 over 9. So you get 4 root 2 minus root 5 over 9. You may have gotten discouraged. We'd only done half the problem at that point. But we've done all the work to do this one too. So the only difference in these two formulas is that becomes a minus. So there we go. Okay. And you could use the argument, what quadrant sine, what quadrant is s minus t in? 4 root 2 minus 5 over 9 is positive, so s minus t is either in the first or the second quadrant as well. I don't know which. Okay, now the next problem, it's the same philosophy as some of the ones we've done. It says, find the exact value of the following expression. Tangent of 25 degrees plus tangent of 110 degrees over 1 minus tan of 25 degrees, tan of 110 degrees. Okay? Okay, so it says find the exact value, so they don't punch in the calculator. That's not what they want you to do. Now, is this a problem we could have done in previous sections? In other words, find tan of 25, tan 110, find tan 25, tan 110, and just work it and simplify. Okay? Is that something we could do in previous sections? The answer is no. 25 is neither a quadrantal nor a reference angle in a special, or has a reference angle in a special triangle. 110 is not a quadrantal, and it's also the reference angle of 110 is what? 70 degrees. That's not one we can do with a special triangle. Okay? So in its current form, I cannot simplify this by finding tan of 25 and tan 10. It says exact value, which means don't use the calculator. Right? But what does this look like? In its current form, I can't do anything. Can we rewrite it another way? This looks just like the formula here with the black plus and the black minus here. Looks just like this. If I can't do anything with it in this form, this is equal to this. So if I rewrite this in this form, maybe we can do something with this. That's the idea. Notice in the previous problem with the, which one was it? With the sine, right? They gave us this, which we couldn't do anything with, and we rewrote it this way, and we could do something. In this problem, this looks like this, and we're going to rewrite it this. I want you to understand, you can go either way. You can not be able to do this and write it this way, and you can. Or it can look like this, and you can't do anything, so you rewrite it this way, and you can, right? The identities work both directions, right? So I can't do anything with this, but this is equal to this, so this would be the same thing as tangent of what, right? So it's a plus here and a minus here. It's the black, so it's the black here. It's tan of the sum of the angle. Right? So it's tan of A plus B, because this matches the black here. It's the plus and the minus here, and so it's the plus here. So that's tan of A plus B. Now what is that? Let's add the angles together. 25 degrees and 110 degrees is 135 degrees. Now is that an angle we can do? Is it a quadrantal, or does it involve a special triangle? Well, 135 degrees is in the second quadrant. 135 degrees. Now, what's the reference angle of 135 degrees? 180 minus 135 is 45 degrees, and we're in business, okay? So this didn't involve a special triangle or quadrantal. 110 degrees did involve a reference angle with a special triangle or a quadrantal. But when we use the formula to go back to this side, the angle I get does involve a special triangle, so we can figure it out. So what are the numbers on the 45, 45, 90? It's 1 square root of 2 There's a negative on the x value because we're in the second quadrant. And what's the tangent? Opposite over adjacent, which is the negative. Okay? Okay, so the next two problems are identities. All right, so the first one says, verify this identity, tan of x minus y minus tan of y minus x is 2 times tangent x minus tangent y all over 1 plus tangent x tangent y. Wow. We want to verify that equation's an identity. Okay, so what's the procedure? We need to start on one side and work our way to the other. And again, a philosophy I always try to use is which side's more complicated, because it's easier to destruct than it is to construct. You know, simplify versus start with something simple and build up. But both sides are rather complicated in terms of just their expressions. I mean, here you have a difference of things, and here you have a quotient. But another way you can argue more complicated is don't look at the expressions themselves, look at the angles. Notice on the left I have an angle of x minus y. I also have an angle of y minus x. And on the right, what are my angles? X, y, x, y. So the angles on the left are more complicated than the angles on the right. Right? So that's another thing you can think about. So on the left, I have a difference of angles, and on the right, I just have individual x's and y's for angles. What do these identities do for you? It takes sums and differences of angles and breaks them down into the individual angles. So here you have a minus b or a plus b. Here you have a, b, b. Here you have a minus b. The angle's a minus b, but over here you have a, b, a, b, right? So this is a clue, something reasonable to try, is start on the left-hand side and break those up so I just get x's and y's. And what makes me think to do that? Because on the other side, my angles are just x's and y's. So I'm going to start on the left, write down the side you were starting with. Okay. So don't write down equals that. I don't know that it equals that yet. I'm going to do stuff to this to work my way to that. Right? So I'm going to use the tan of x minus y formula here. So tan of x minus y is tangent of x minus tangent of y over 1 plus tangent of x, tangent of y. So A is x and B is y. So tan of x minus tan of y over 1 plus tan of x, tan y. That's just this one. That's that one. And then minus, I would do the same thing with tan of y minus x. So they're switching, instead of x is a and y is b, we're switching. So a is y and b is x. It's still tan of y minus x. It's the blue formula. So that's tangent of y minus tangent of x over 1 plus tangent of y, tangent of x. So tan of x minus y, x, y, x, y, that's this one. And then tangent of y minus x, it's y, x, y, x, that's that. Now, it looks like we're on the right track, because if you look at the denominator we got on both of these fractions, it matches the denominator we're trying to get to. So that looks promising. So I have 1 plus tan x, tan y. I'm not going to add these two fractions together. So to add, well, I'm subtracting the fractions. So you get tan x minus tan y. Now, be careful. The minus, it's minus the whole thing, so you have to distribute the minus sign. I get minus tangent y, and then plus, minus minus is plus tangent x. Okay, so I'm going to continue over here. So I have 1 plus tangent x, tangent y in the denominator. Notice I have a tangent x plus a tangent x, that's 2 tangent x. I have a negative tan y minus tan y, that's negative 2 tangent y. And we're basically done. To make it match the other side, all we have to do is factor a 2 out of the numerator, and we are done. It's a lot of writing, but it wasn't a very hard problem. But what's the key on this problem, like it is with most identity problems, figuring out where to start, or just finding something to start. Notice, I didn't even look over on the right-hand side. Well, I did just to see if I was on the right track. But I didn't use the right-hand side to help me, get anywhere, right? I recognize, well, in the very beginning I did. The angle here is x minus y, the angle here is y minus x. The angles on the right-hand side are x's and y's. So let's break up the angles. So that's what made me do that, was compare the angles on the left with the angles on the right. But once I used the identities to break up the angles into x's and y's, I just said, well, be aware tan x tan y is the same as tan y tan x. So the denominators are the same, right? And I just subtracted fractions and did some algebra, and then I said, oh, okay, we're done, okay? So I did use compare the left-hand side to the right-hand side to figure out where to start to break up those angles. But after that, I didn't use the right-hand side to actually do the work. Right? But sometimes it is helpful to look and see what you're trying to get to. That'll give you an idea of what to do next. Okay, so the next one is another identity problem. This one's called a cofunction identity. It says show cosine of pi over 2 minus theta is equal to sine of theta. And they give you a hint here using the cosine difference formula. But it's the same argument I used here, right? On the left-hand side, I have angles pi over 2 and pi over 2 and theta. On the right-hand side, I just have angle theta. So if we could break those up into pi over 2s and thetas, maybe we can do this. So it's the exact same thinking I did here. Here the angles were differences. On the right, I just had x's and y's. Here the angles are difference. On the right, I just have a theta. So I want to break those up. So I'm going to start with the left-hand side. Cosine pi over 2 minus theta. Well, if I use the cosine a minus b formula, the one in blue, that's cosine pi over 2 cosine theta plus sine of pi over 2 sine of theta. Okay? So I'm using the cosine a minus b formula. Okay? So cosine of a minus b is cosine a cosine b plus sine a sine b. Okay? So that's my a, pi over 2, and b is my theta. Now there are 4 things here to find. Now cosine theta I can't find. I'm just going to leave it cosine theta. But notice the 2 trigonometric functions with the pi over 2, we can figure out those values. Right? We can find cosine pi over 2 and sine pi over 2. Pi over 2 is a quadrantal angle. Remember what I mentioned before. If you have an angle in radian measure that has a simplified fraction coefficient, and you have a pi in it, right? The fraction here, the coefficient's a half and a half. I know that's a quadrantal, right? When the denominators are 1 or 2 in radian measure, you know it's a quadrantal. Well, we've been doing those with the unit circle. Here's pi over 2 radian. Pick the point 1 unit from the origin, that's 0, 1. And remember, the x value is your cosine. Your y value is the sine. And so you have 0 cosine plus 1 sine, and lo and behold, that's sine, because that's 0. 0 plus 1 times sine is sine, and you're done. That's the other side. Again, starting with the right-hand side, it wouldn't be very productive because it's so simple. What would you do with it to try to get to here? So it really made sense here to work on the left-hand side and use the hint told you to do that. Start on the left, use the difference formula for cosine. So that pops right on that. Now this identity shouldn't be a surprise to you. Now, when we first talked about right triangle trigonometry, we didn't do radians. But think about what this is in degrees. It says cosine of 90 degrees minus theta is sine of theta. You can do this identity in degrees or radians. Okay? So if you think of this as in degrees, it's cosine 90 degrees minus theta sine theta. Think about the right triangle stuff we did. Here's theta. And if I call this, it doesn't matter, A, B, and C. Okay? What was the sine of theta here? The sine of theta in my picture is opposite over hypotenuse. It's B over C, isn't it? Okay? Now, where is the angle 90 minus theta? Well, in a right triangle, the 2 acute angles are complementary angles, right? So if this is theta, this one is 90 minus theta, isn't it? Right? The two acute angles, the two have to add up to 90 degrees, and they do, right? 90 minus theta plus theta is 90 degrees. What's the cosine of that angle? It's the adjacent over hypotenuse, B over C. That's what we got when we did that. So from a right triangle tree, we've already seen that. Okay. You could also write it this way. Cosine theta is sine of 90 minus theta. Right. The cosine of theta is A over C. The sine of this one is A over C. So it doesn't matter whether you have the theta here, the 90 minus theta here. You can switch them. Bottom line is they're complements of one another. That plus that is 90. That plus that is 90. Okay. And there are other, the other cofunction identities are similar. Right? You can do secant and cosecant, and you could do tangent and cotangent. Right, if you do this picture I did right here, like cotangent of theta is A over B. Tangent of this is A over B. So students always say one with the reciprocals, sine and cosecant are reciprocals, cosine and secant are reciprocals, and tan and cotangent are reciprocals. They say, why aren't sine and cosine reciprocals? Why did they name them that way? Notice here the names match up the way you would think, right? Sine and cosine was the original problem. You can do secant, cosecant, tan, and cotan. So if you think of it in terms of this property, they're paired up, sine, cosine, secant, cosecant, tan, cotan. With reciprocals or not. Right? If we named the reciprocals, if we had defined sine and cosine to be reciprocals, they wouldn't be paired up here the right way. So, okay, so that's that one. And then number 53 here says, let me write the problem. Sine of arc sine of x plus arc cosine of x. Remember, arc sine and arc cosine that just means sine inverse and cosine inverse. Okay, that's just another name for those. So just be aware that sine inverse and arc sine mean the same thing. Okay? Same for all 6 strip functions. Okay, let's think about what we have here. The instructions say, write this expression as an algebraic expression. Okay, what they mean is get rid of the trig functions and the inverse trig functions. So just have x's. No sine x or cosine x. That's what they mean by algebraic expression. Get rid of the trig functions. Now x is going to be in there, but not the trig function. We don't want the trig function. Now let's think about what we're doing here. So x is a number. Now how do I know x is some number? Because you take arc sine of a number, and that gives you an angle. You take arc cosine of a number, and that gives you an angle. So this is an angle and this is an angle. If you add 2 angles together, you get another angle. And when you take sine of an angle, you get a number. Okay, so the answer here is a number. That's why you can write it as an algebraic expression. It's just a number. So we're not going to have trig functions in the answer. Okay, so I'm not worried about the sine yet. Let me investigate these 2 angles here in the parentheses. Okay, let me call this one, I'm just going to call this A. So arc sine of x, I'm going to call A, angle A. And arc cosine of a number to angle, I'm going to call arc cosine x B. Okay? So I know this is arc sine of a number is an angle, I'm going to call that angle A. Arc cosine of a number is an angle, I'm going to call that angle B. Now, remember when we did the inverse trig functions section, we wrote 2 facts. I don't really need to know the quadrants here, but if arc sine inverse of x is A, that means sine of A is x. Right? And if arc cosine of x is B, that means if cosine inverse of x is B, that means cosine of B is x. Right? Okay. Well, I guess it depends on whether we're positive or negative. Okay, so we may need more information here. Give yourself some room. So let me come back to the original problem. Right? Let me rewrite this as A and this as B. So I have sine of A plus B. Right? Sine. Right? So this is A and this is B. So I've written a sine of A plus B. Now I did this on purpose. I called this A on purpose and that B on purpose because now what does this look like? It looks like my formula here, right? I don't know angle A plus B. I don't even know A, right? I don't know where those are or anything. But the sine of A plus B, well, I can rewrite sine of A plus B using the black plus there. That's sine of A cosine of B plus cosine of A sine B. I'm using the identity here. Sine of A plus B, sine of A cosine B plus cosine A sine B. Okay? So from this, if we can just find these four things, I've got my answer here, right? So this is sine of A plus B. So if I can figure out those four blanks, I've got my answer. Now two of them I already know. Sine of A is x. And cosine of B is x. Right? So two of them we know. Now I need to find the cosine of A, which I don't know, and the sine of B, which I don't know, right? Okay, so I don't know what x is, right? If x is positive, arc sine of a positive, A is in the first quadrant. But if x is negative, A is going to be in the fourth quadrant, and it doesn't say. Right? So let me just draw a triangle picture here. Let me just work it from the first quadrant. Suppose A is in the first quadrant like this. Suppose A is in the first quadrant. Well, sine of A, think of this as x over 1. Right? Sine is opposite over hypotenuse. Right? Sine is opposite over hypotenuse, opposite over hypotenuse. Use Pythagorean theorem to figure out the other side. This side squared, right, if I call that q, I don't want to say x because this side is x because of the x here. So q squared plus x squared is 1 squared. Q squared plus x squared is 1 squared. That's Pythagorean theorem. So q squared plus x squared is 1. 1 squared is 1. Q squared is 1 minus x squared. Subtract x squared from both sides. So when you introduce the square root, q should be plus or minus the square root. But if I assume we're in the first quadrant, notice q is positive. It's the square root of 1 minus x squared. Now you cannot simplify. You can't take square root of 1 and square root of x squared and say that's 1 minus x. The roots don't work that way. You can't take the square root over subtraction like that. Okay, so this side is the square root of 1 minus x squared. Okay. Now I'm assuming x is positive. That's why I drew this in the first quadrant. Now what if x were negative? If x were negative, right? Remember, when you say arc sine of x is A is either in the first or the fourth quadrant. That was the definition of the inverse trig function, arc sine. If x is negative, sine is negative, and you're in the fourth. But wouldn't the picture look like this then? It'd be opposite over hypotenuse. We still would have found that side, so it would still be positive. Okay. So whether x is positive or negative, the picture's in the first or the fourth, I'd still be finding that same side, and that's what it turns out to be. Right? So if I go back over to my blanks here, I need the cosine of A. Well, what's the cosine? It's this side over the hypotenuse. Whether I'm in the first or the fourth, right? Adjacent over hypotenuse, adjacent over hypotenuse. So the cosine of A is the square root of, the square root of 1 minus x squared. Okay, so that's cosine. Now we need to do the same thing with B. I need to draw a picture for B. Now again, let's assume x is positive. If x is positive, cosine of B, when you say arc cosine of x is B, when you do arc cosine, that means the angle's either in the first quadrant or the second quadrant. Let's assume we're in the first quadrant here. So I'm going to assume B is in the first quadrant for now. Well, cosine is adjacent over hypotenuse. Think of that as being over 1. So cosine is adjacent over hypotenuse. Well, if we do the same thing to find this side, if I call that q and work it out, you're going to have x squared plus q squared is 1. It's the same thing. So you're also going to get the square root of 1 minus x squared here. If you work it out, you get the same thing. Right. Now, what if x were negative? If x were negative, cosine is negative. Remember, arc cosine of a number gives you an angle. The angle's in the first or second. So what if x were negative and my angle B were in the second quadrant like this? Okay. Well, cosine is adjacent over hypotenuse. Again, I'm assuming x is negative, so this would be negative, which makes sense. But how big would this side be? It'd also be 1 minus x squared, wouldn't it? Because you use the Pythagorean theorem. Notice it's positive root and positive root. Both these sides are positive, because in the first, y is positive, and the second, y is positive. So it doesn't matter which quadrant you're in, you're going to get the same answer for that side. Just like here, it didn't matter which quadrant A was in, I got 1 minus x squared or 1 minus x squared for both sides. So what's the sine of B? It's opposite over hypotenuse, opposite over hypotenuse. You get the same answer It's square root of 1 minus x squared. So notice what we get here. Oh, this is so disappointing. I get x squared here. Root 1 minus x squared times root 1 minus x squared is 1 minus x squared. And we did all that work to get the answer of 1. Well, that's disappointing. Okay? So this one's a little more complicated, but the key here is realizing that is an angle. Call it something. That is an angle. Because when you take arc sine of a number, arc cosine of a number, and those give you angles. So call that angle A, call that angle B, and then realize you're finding sine of A plus B. There's sine of A plus B. If you use your double angle, your sum and difference formulas, your sum formula for sine, A plus B, it turns out to be this. Two of those we knew from this. If arc sine of x is A, sine of A is x. If arc cosine of x is B, cosine B is x. So both of those go here. And then to do the other two, you draw your triangle pictures from this and this. Figure out the other side, plug it in, and it's simplified to 1. So there's section 5.4.